Well, look at the time. It's 10:10 already, and I did say that we will start around 10:10 p.m. So here we are. Anyway, and welcome to this stream. Yeah, where we will be discussing the following topics for today. We will be discussing impulse, momentum, and collisions. If Just in case that we did not tackle everything in one go, there's always another time, maybe tomorrow or something. So I know it's I've supposedly turned this into every course outcome. There's one live stream, but many things happened, and I ended up only doing one, and that was last month. But hey, at least here we are today, discussing CO4. If you could hear the air conditioning unit in the background, then just pretend that you don't hear that, because I hate that. You can't really do anything about it because this microphone, and I need to make myself cold while doing this because I don't like sweat. Sweat sucks. Okay, so first thing, there's impulse. Yeah, impulse. It's hard to distinguish the I from the L. Impulse is what it is the product of force applied over a period of time. Okay, so force times the amount of time it was applied. And no, it's not a flex on the aircon, okay? That's why would anyone flex that? I don't know. But hey, impulse is the product of force and time. It could also be interpreted as the change in momentum. Yeah, that's pretty much it. Yeah, just change in momentum. That's what impulse is. And momentum, okay? Momentum is the product. It's the product of an object's mass times its velocity. Okay, and since we know that velocity is a vector, okay, and that means that momentum is also a vector, and momentum is often represented with a symbol. You call it p. Okay, it's a small p. Why it's called p, I don't remember, but it has something to do with tether, or to keep on moving. I have no idea. This is physics, not etymology. Okay, and yeah, this is one way of writing momentum. To begin, we could start with an example. Okay, let's say we have an object. I can't think of an object. Let's say it's a basketball. Okay, let's say it's a basketball, and it's very orange. Okay, and then it has a velocity of, no, actually, yeah, it has a velocity of around, how fast do basketball players throw these things? It's faster than running, certainly. So let's say it's around 20 meters per second. And let's say that the basketball's mass is around, how heavy is a basketball? I have no clue. So let's say it's 1 kilogram heavy for a basketball. I don't know. Oh gosh, that's a ring. Okay, let's say it's 500 grams. Okay, say it's 500 grams, and 500 grams is around half a kilogram, 0.5 kilograms. What is this basketball's momentum? That's easy. We just multiply the mass right here. Wait, I should have written V here. We multiply the basketball's mass, m, and then we multiply it by its velocity, v. and then we'll get the magnitude of momentum at least. And then, okay, the mass is 0.5 kilograms, and its velocity, at least the magnitude of the velocity, is 20 meters per second, giving us a momentum of 0.5 times 20, that's 10 kilogram meters per second. By the way, this right here is the unit, okay, at least the SI unit for momentum, kilogram meters per second. Wow, weird. Another problem, okay. Let's say that there is a baseball, okay. There's a baseball right here. And then we'll maybe color it with the stripe. Is that a baseball? Is that a nice looking baseball? I have no clue. And then you have what's brown? Okay, let's call that brown. And then you have a bat, or just a long stick that you just a long stick right there. Oh gosh, I messed up the colors. Is that? Wow, a stick. Amazing. And then, okay, you have a stick right here. And then, this ball, right here, this baseball, is moving to, let's define some coordinates first. Let's say that this direction is the negative direction, and this direction is the positive direction. The upward is the positive direction, and the bottom is a negative direction. Okay, let's define our directions as this. Where do I put it? Let's put it here, because it's cool. So our ball here is traveling to the left with a velocity. Alright. Its velocity is that it's traveling to the left at, I have no idea how baseballs travel. Let's say it's 50 meters per second. Yeah, I don't know if that's fast or slow. Okay, as long as the math works out. Okay, this is our velocity. Well, I mean, since it's in the negative direction, okay, let's, to be more specific, it's negative 50 meters per second. Okay, this is the ball's velocity, and it has a mass of, I have no idea how baseballs weigh, 0.125 kilograms. Wow, nailed it. Or maybe 0.13. Let's round it up. 0.13 kilograms. And it's traveling to the left. Okay, so it's going like this to the stick, and then it hits the stick. Okay, it hits the stick, and okay, let's say that you're holding the stick, and then you whack at this ball really hard, and then give me a moment. Oh gosh, that's not right. And then you hit the ball really, really hard, and then it goes flying in another direction. I hear someone yelling outside, and I am concerned. Oh no. I think I left the dog outside, but okay, let's pretend we didn't hear that. Alright. I hope my mom is not yelling at me, because it's mean. Okay, and then it hits the ball, okay? And then we hit the ball with the stick, and then it goes flying back at a much higher velocity. It's around 90 meters per second in this direction, okay? In the rightward direction, so it's a positive one. And then let's say we want to calculate what's the impulse on the ball. Please don't tell me she's going fast. If this stream suddenly goes black. You know what happens, parents. Very fun. Okay. We know that impulse, as we have mentioned earlier, is the change in momentum. Okay. So first, what's the ball's original momentum? Okay, that's easy. We have our velocity, we have our mass. So the initial momentum of the ball is. I should pick another color. Let's pick blue. Blue. I like blue. Blue is a calm color. Okay. We multiply. Wait, no, I'm stuttering. It's the mass multiplied by its velocity. Wow, America or France? I don't know. And where is the right color? Oh gosh, where's the right color? Here. It's equal to the mass of the ball, which is this. And then we multiply it by the velocity of the ball, which is this. I am screwed. I'll do a little, activity for you. You multiply this while I am out for a bit. Yeah, just multiply that first, real quick, and then you could chat me the answer. Hello, kids. We are back. Okay, so what did you get for an answer after multiplying them? Is this chat even on? No? Is this chat accurate? No, it's not. Okay. Okay, direct message. Weird way to do it, but okay, I'll take it. And then, for an answer, where is my calculator? Goodness. Everything's gone wrong. Here it is. Alright, the object's initial momentum would be, after multiplying them together, we get negative 6.5 kilogram meters per second. Hi, this is the object's initial momentum, and then we could figure out the final momentum, right, after it gets hit by the stick. We multiply this. Where did it go? I have no clue. We multiply this by the final velocity. Why isn't it working? There we go. And then after multiplying this, you should get PF. Alright, this is just the math part, so it's, of course, it's tedious. I'm sorry. Multiplying them together, times 90. Okay. It's around positive 11.7 kilogram meters per second. So it was asking what is its impulse. What was the impulse done by the stick on the ball? So it's easy, all right? Since it's the change, okay, we know that change is the impulse is the change in momentum. Okay, we subtract the final momentum from the initial momentum, which is subtracting this 11.7. Okay. Then we subtract it by negative 6.5 kilogram meters per second. This, the impulse should be 6.5. There we go. 18.2 in the same units, of course. If I recall correctly, impulse could also be written as J, I think. I'm not sure, but it's just a symbol. So this was the impulse done by the stick on the ball. Yeah, that's pretty much it. Also, fun fact. Here's a fun fact. Did you know that force, as in force like mass times acceleration, force is actually the change in momentum over time. So you may encounter force as, you could think of force as impulse over a period of time. Just a little fun fact there. Now we could move on to something called collisions. Collisions, I have no introduction for collisions. But it's kind of common sense. When things collide, there's a collision, and there are two kinds of collisions. I think we've only discussed one so far in the lectures, but it depends on which class you're in. But there are two types of collisions. I don't know if I've spelled it right, but hey, here we are. And then, there are two types of collisions. The first kind of collision is the elastic collision. I'll tell you what all these words mean after enumerating all of them. Why do I even put that? And then we have the inelastic collisions. So what the heck do these mean? What does it mean for a collision to be elastic and for a collision to be inelastic? Okay, that's simple. If a collision is elastic, that means that the total kinetic energy before the collision is the same amount as after the collision. In other words, this means that, it just means energy is conserved. Well, to be specific, kinetic energy. That's what it means to be an elastic collision. So an inelastic collision, on the other hand, is when the I'll make my pen smaller. I hate it chunky. Is when the total kinetic energy of the two objects before the collision is greater than the total kinetic energy after. Which, in other words, means that kinetic energy is lost. I'll just copy kinetic energy from here. Okay, there. Kinetic energy is lost. And there are actually, two kinds of inelastic collisions. We have the perfectly inelastic collisions. Let me just fix my handwriting. And there are also partially inelastic collisions. No, that's not right. Right. So what's the difference between a perfectly inelastic and a partially inelastic? I just realized I spelled it wrong. Let's just sneak an L there. Okay, I'm not a grammar man, but for a collision to be perfectly inelastic, it means that there is a maximum loss in kinetic energy. And that also means that when the two objects collide, they tend to stick together. Okay, colliding objects stick together. Colliding objects stick together. Right. And the general thing between all these kinds of collisions is that momentum, right? At least linear momentum, is conserved. Always. So it's possible that you're wondering how come in some kinds of collisions kinetic energy is conserved, okay? Like, according to the law of conservation of energy. How about when kinetic energy is lost? I thought that energy is supposed to be conserved. So why did we lose some kinetic energy in inelastic collisions? That's perfectly okay. We're not violating any laws, even if inelastic collisions happen. Because let's say we have two objects. Let's have a red object and an orange object. And then let's say it hits the orange object, and let's say that they stick together. Where did you know where there is some loss in kinetic energy, but that's perfectly fine. The energy, I some of the energy went, if let's say we did this in your usual environment. Chances are that some of that energy was lost as a sound energy, or maybe if you measure the temperature of the balls after the collision, there's a possibility that they're hotter because some of the kinetic energy became, what they call this, thermal energy. Let's do some examples. Alright, let's do an example of collisions. Let's say that we're on a track. Right? We're on a railroad of some sort. I have no idea how to draw, but that's the best I could do. And then we have a blue train, blue cabin of some sort. I cannot draw a blue cabin. Okay, let's. Alright, there, nailed it. A cabin, a cart. I don't know what words mean. Okay, like, rails. the thing that contains people. Yeah, it's let's call it a car. Okay, boom, genius. And then we have another car. Oh gosh, I. Alright, that's. Trust me, that's a car. Just erase these real quick. Okay, and then this. Let's say that this blue car is much heavier than the red car. Okay, and then this blue car was originally traveling at some velocity to the right. Okay, some velocity v I v1. Let's call it 10 meters per second to the right, and it has a mass of around. How heavy is the car? Let's say 1,000 kilograms. Actually, no. Let's use another symbol. We could use this convention. Okay, V for final velocity, and U for initial velocity, because I cannot bring myself to write VI1 and VI words. How do they work? But just to introduce some new symbols. Okay, U initial, V for final velocity. Let's say that the blue car's initial velocity is 10 meters per second, and it has a mass of, let's say, 2,000 kilograms. And then we have another red car that's initially not moving. Okay, so that means its initial velocity is 0 meters per second. And then we have, let's say that the mass of this red car is, let's say, 1,000 kilograms. And then, in a tragic accident, this blue car hits the red car, and then it sticks to it. Okay, the blue car sticks to the red car after the collision. So this is a case of a perfectly inelastic collision. But whatever. Now, after sticking together, they have this common velocity. Let's use purple. They are moving at this common velocity, v. And then we want to know what this v is. So, let's calculate. Okay, let's first calculate the original momentum of the blue car and the momentum of the red car. Okay, so the momentum of the blue car is 20,000 kilograms. Wait. Okay, let's just write it directly. 20,000 kilograms times 10 meters per second plus a fat zero, because 1,000 kilograms times 0 meters per second, and it's just a fat zero. And okay, this is the initial momentum of the system, and the final momentum of the system would be 20,000 kilograms. You see, since they're moving at a shared velocity, okay, since they stuck together, they should be moving at the same velocity. So that means, V of the velocity, the final velocity of the blue car is equal to the final velocity of the red car. So let's say, and they should be equal to the common velocity, this purple V right here. No, that's not right. And remember, linear momentum is always conserved. So therefore, these two should be equal to each other. Alright, let's start doing some math. I know math is lame, but it's a very important thing in physics. So these should be equal, right? And then we are solving for their common velocity. What we could do here is that we could factor out the v. Right? We could factor out the v. Oops. We could factor out the v. And then divide both sides by this. So we should do a little transpose right here. Just erase some. We divide it. Screw it, just erase everything. And yeah, that's basically it. That's how to compute the, after a inelastic collision, a perfectly inelastic collision, how to find their shared velocity. So if we put this in a calculator, it's going to be 20,000 times 10 meters per second. Right, this would be, oh gosh, right, 1,000 times 10. This should be 20,000 kilogram meters per second, and this would be a fat 0 kilogram meters per second, and then these would be equal to 30,000 kilograms. If we divide it all, or if we jam this in a calculator, we would find out that V is equal to positive 6.6. Wait, how many sig figs is this? 6.67 meters per second. Yeah, so that's how we did it. Now imagine another case. All right, let's do a scenario for an elastic collision. Let's move all the way to this side of the blackboard, and then we zoom in a bit. Alright, what's happening? Okay. Let's say that there is a sphere. This blue is a very blue sphere. And then we have another sphere, which is a bit smaller, but it's fine. Size doesn't matter. We have this red sphere and this blue sphere. And this blue sphere is moving at around, I can't think of numbers. Numbers, how do they work? Let's say 10. No, we keep using 10. That's lame. 30? Okay, that's no. Yeah, fine. Let's use 30 meters per second. Right? It's moving to the right at 30 meters per second. And this blue sphere has mass of, can't think of numbers. Let's say 2 kilograms. 2.5? No, fine. 2.5 kilograms. And then and then we have this red ball moving also to the right at around 20 meters per second. So it's eventually gonna catch up and collide. So don't worry, a collision will still happen. And let's say this is 1 kilogram. Okay, and then let's copy this a bit. Then, okay, if we let this play out, since this blue sphere is faster than the red sphere, it's eventually gonna catch up and hit. Let's assume that we're not scrolling to the right place. Let's assume that what occurs is a perfectly elastic collision where the kinetic energy will be conserved. After the collision, what would the velocity of the red ball, wait, what would the velocity of the red sphere and the blue sphere be? Let's start doing some math again. Right, it's VF, final velocities. Wait, 1, 2, and then we don't know what these are. That's the sad reality. Okay, so let's set up our equations first. We know that momentum is conserved, so the mass of the blue object, let's call the blue object object 1 and the red object object 2. Alright, so mu1, this is the initial momentum of the blue sphere, plus m2u2, this is the initial momentum of the red sphere, is equal to m1v1, this is the final momentum of the blue sphere, plus m2v2, this is the final momentum of the red sphere. Remember that we'll be using u for initial velocity and v for final velocity, because for convenient reasons. And remember, kinetic energy is conserved, so we know, as we could remember, the formula for kinetic energy, the kinetic energy of an object is 1/2 multiplied by the object's mass multiplied by the object's current velocity squared. Right, this is kinetic energy. So the initial kinetic energy of the blue sphere would be 1/2 m1 u1 squared plus, this is the initial kinetic energy of the blue sphere, and this would be the initial kinetic energy of the second sphere, the red sphere, and then this would be the final kinetic energy of the blue sphere after the collision, and this will be the final kinetic energy of the red sphere after the collision. Let me drink some water, stay hydrated. Then, I just realized this entire time that it's turned off. Okay, so let's say we want to find these variables. We're looking for no, that's not right. VI, and that's not how you draw an ampersand. Yeah, we're looking for these variables. So here's what we could do first. Okay, this is for a general case. Okay, before plugging the numbers in. So, we're basically deriving on. We're deriving an equation live. Yes, I am actually doing this. So, let's say we want to solve for VI, right? V1, the final velocity of the blue sphere. Now, this is where it gets really messy. Okay, so we'll start working. First, what we could do is we could transpose this term to the other side. So it's gonna be minus is equal to m1v1, and then we could divide it all by m1, so we could isolate that poor thing, m1. So we have final velocity of 1. And then what we could do, okay, you see this variable, what we could do is we could plug it in. straight right here. Yeah, we're gonna do it. We're gonna plug it in there. Let's make it a little neater. What we could do is transpose. Huh. You know what? Nah, let's... Actually, you may have noticed there's a 1/2 term in every single term in this equation. So, to make things a lot simpler, we could just multiply everything by 2 and this equation is still valid. Alright? We're just multiplying everything by 2. And then we could move it in closer. So, to save space. Because we are kind of running out of blackboard, and that's terrifying. So, what we could do here is transpose this here, right? Yeah, we could transpose it to the other side, so it's gonna be oh, that's not right. So we have, oh gosh, what are we doing? So we have this equation, and then we could divide it all by m, and then find the square root. As you could see, these are both equal to each other, so we could do some substitution and jam this in right here. Then we start solving for v2. First, we square. Yeah, I know this is a long way to do it. We square that. Oops, we haven't done that quite yet. Then do this. Okay, we distributed the square, and then cancel these out. Okay, we multiply each side by m1, so it's gonna be just a single m1. Then we could move this the other side, multiply everything by that term, and then this is a really boring process, I swear. M1 squared U1 squared plus M1 M2 U2 squared minus, wait, is this M1? I don't think that's supposed to be M1. It's supposed to be 2. Mistake 7. M1, no, that's not the right color. M1 M2 V2 squared is equal to whatever this is when we square it. It's hard to square trinomials. Okay, it's really lame, it's really boring. But here's what we could do to make it a very neat binomial. We could factor this term out. Okay, if we focus on this area, we could factor out the m2 term. Okay, we could just factor out the m2 term, and we get something neater like this. Oops, I am technologically inept. Okay, so right now it's just a binomial, which makes squaring it a hell of a lot easier. Okay, first we square the first term, m1 squared u1 squared, and then we multiply these two by each other and multiply that by 2. That's 2. Oh dear me. By that, by this, plus the square of this term, which is m2 squared . 2 u2 minus v2 squared. Okay, so we have this equation now simplified, well, expanded. Now you may have realized that we could cancel these terms out. It's cool. Makes everything a lot easier. And yeah, that's it. Then here's another thing. You see this? What we could do is we could factor out m1, m2. So we could just hit them with this 1 m2 u2 squared minus v2 squared. Why? I hope that makes sense. You know, we just factored out these. It's equal to, just copy this entire dang thing. And as you can see here, okay, you may have realized something. It is a square. Okay, it's the sum and difference of a binomial, because you know, just look at it. Alright, it looks familiar. And what we could also do is we could move the entire thing to the right, because we are running out of space. I know that mass got amputated, but we could just rewrite it. If it makes it better, I could send this entire board as an image file, and then, you know, send you a copy later for later reviewing. You'll never know. M1, M2. We break this down into U2 minus V2 and U2 plus V2. You know, I hope that made sense. Minus this. Now here's a thing you may have also realized as well. You could factor out the u2 minus v2 term out of all of these. So it's gonna be, oh boy, this is gonna be painful to look at. M2, oh boy, u2 minus v2. You know, we factor that out by everything by 2 times m1 u1 plus m2 u2 minus v2. Alright, we just factored out that term from all the terms here. And you may have realized, again, you may have noticed that we could just cancel these out. Oh gosh, what is it? We could cancel this out, we could cancel this out, and that out. So we will be left with this equation. M1 multiplied by u2 plus v2 is equal to 2 m1 u1 plus m2 u2 minus v2. Alright, we're left with this, which looks so much simpler in so many ways. And then we could distribute this. We could distribute that. We can do this. M1 u2 plus m1, we just distributed v2, is equal to 2 m1 u1 plus, we're gonna distribute this again, m2 u2 minus distribute m2 v2. Now we could we could put all of the terms with v2 in one side, so we could just move this here move this here, and then transpose this to the other side. Okay, and then we could factor out v2 from these terms. So it's gonna be v2 m2 plus m1 is equal to this entire thing that I'm just gonna copy because screw that. And then we could divide all of these by this. Just divide both sides by that. And then it'll cancel out. And then we're gonna be left with this. The final velocity of the second object would be equal to whatever the heck this is. Yeah, we just derived a full equation to find the final velocity of v2. So we have v2 checked. But then again, we need to find out v1. But it's okay now because what we could do is get this, and then we could substitute it to, here, or here at least. We just pull it all the way down here. Right? We'll just substitute this with, whatever the heck that is. Actually, we could, yeah, everything's fine. But to make it simpler, wait, no, we could, let's just use the other one. It hurts to look at. Let's just use this one. Okay, let's use that. And then we substitute this. Wait, no. This is just mathematical convenience, but the idea is still there. It's just plugging in the equation. What could we do? No. Stay there. We transposed this term. We transposed this term to the other side. Then we could divide it all by m2. We could substitute this to here. This is a big boy. Okay? Then we could start doing math again. It's painful math that make me want to obliterate my kneecaps. Right. We're isolating v1. It looks so ugly mathematically. I hate it. Okay, we could do this. We could multiply this side by m2. So, whoops. Let's copy this entire thing here. Multiply all of that by m2. Good thing we could copy and paste, because if we can't copy and paste, I would have lost my sanity already. And then we could distribute that, just like we should do with money. Haha, communism, very fun. Nah, just kidding. It's a ridiculous joke. Communism doesn't work. And then stick this term right here. Right, just distributed the m2 term. Then we could send this to the other side. No, wait, we multiply. No, just kidding. We move this to the other side. Right, move these terms. No, what are we doing? Move these here, alright, and since we're transposing, we change the signs. Okay, this is getting a little messy, but it's fine, we can do this. Then, so we could, so just so we could have the ability to, you know, mix these things up, we need to multiply m2 plus m1 to both of these. So we could put all of them over one denominator. It's gonna be this, divide that, minus right, we just multiplied this to these so we could have it under one denominator. And we are running out of space, so let's just move a little bit to the right. I know the M got amputated. It's always the poor M that gets amputated. Oh well, it's fine. Props to that one viewer who's, you know, who has the balls to stick through all of this math. Good job. Then, oh wait, we're about to hit the bottom. Oh no. Alright, let's get back to this one. Minus this times this. Okay, if I find out that this one viewer is actually my own phone, I'm gonna cry because this is just sad. This is just sad and lonely. Yeah, we have that, which is all equal to this. Then, what we could do is start distributing these and start canceling out terms to make everything neat. Yeah, I hope that's cool. This is gonna be a long way. Okay. Just some math. It's just some math. No, nothing to be afraid of. It's just numbers written on the wall. There's nothing scary about them. Oh boy. Let's zoom in a bit. I just make a sign of a cross because we're about to go into some deep stuff. 2 M1. No, that's wrong. It's the wrong sign. 2 M1 U1 plus M2 squared U2 minus M1 M2. We just moved it. You know, remember that multiplication is commutative, order doesn't matter. And then we distribute this, which would be M1 M2 U1 plus, no, it's a minus as well. It's minus because of the sign here, remember. Where's the right color? M1 squared U1 minus I am gonna shoot my kneecaps. M2 squared U2 minus M1 M2 U2. That's so many letters. I don't like letters. Then all under this bad boy. Cool. And then, no, just keep it. Oh gosh, what's happening? That probably hurt your eyes. I'm so sorry. And then we could start canceling out some terms. So we have positive m2 squared u2, and we have negative m2 squared and u2. So we could just cancel these out. What else could we cancel out? This and this No, this and this kind of cancel out. So cancel that out, and since it's 2, subtract. And then we have this and this. We're subtracting it again and again, so we could just put them under one term. We just multiply that by 2. Oh gosh, it's messy. Wait, let's zoom in a bit. Minus 2. Okay? And then we have... is that right? Okay, what happened to the other one? Yeah. Everything's going fine. And remember that all of this is under. Alright, let's rewrite it without all the ridiculous clutter. Negative 2 M1 M2 U2. This is so messy. Minus M1 squared U1 plus this. We're gonna rearrange it so M1 comes first. M2 U1. I hope that's all of it. All over. Remember, addition is commutative, so we'll just change the arrangement of those to make it look nice. And we have that, which is equal to this. Where's the paste? Oh gosh. There. And then we could divide both sides by negative M1. Right? We could divide both sides by negative M1. And then we could start cancelling out some terms. We cancel that. We cancel this. And we cancel this. And this turns into a plus sign because we did that. And there we go. If we rewrite it again, we'll end up with 2 M2U2. Oh right, I almost forgot. We changed that to a negative sign. Plus. Okay, everything's still fine. Okay, everything's still fine. Everything's still fine. It makes sense. Plus M1 U1 minus M2 U1 all over M1 plus M2. Okay, we're done. So now we have an equation for M1. For the final velocity of the first object, which is this, and we have an equation for the final velocity of the second bread object, which is this, and yeah, it looks alright. Okay, so we could just bring this all the way up here. We've gone such a long way. This is equal to V1, and this would be equal to V2. Go somewhere here in the middle. That was so messy and disgusting. Okay, let's hope we never do that again. Nah, just kidding. We'll do a lot more of these kind of things in the future. Okay, so we have these equations. We have solved for V1. We have solved for V2. Now all we need to do is plug in the numbers. Okay, so we have M1 as 2.5 kilograms. U1 as 30 kilometers, 30 meters per second, kilometers, yes. M2 would be equal to 1 kilogram, and U2 is equal to 20 meters per second. Of course, don't forget the sign. Okay, there. So what I want you to do is put these in your calculator and see what happens. Right? I'll just join along. Okay, I'll put it in the calculator as well. Typing 2. Oh gosh, this is messy. Is anyone out there? Help me solve this. No, just kidding. I'm alone. 1 times 20 plus 2.5 times 30 minus times U1 30 plus the sum of their masses, which is 3.5. So what I got in my calculator, I hope is correct, is 224.286 meters per second. Positive, of course. Hopefully. And then for the second one, we have 2 times... Oh my gosh. 2.5 times 30. I got 4.286 meters. Oh gosh, this is the wrong color. Meters per second. Okay, that's cool. Huh? 27.14. Oh, I must have put it in the calculator wrong then. Wait, let me use my phone's calculator then, since I don't trust myself enough to put the numbers in correctly. Wait, let's do it again. 2.2 times 1 times 20 plus 2.5 times 3 minus. I got 24 again. Interesting. There's only one way to settle this. There's only one way to settle this. We have this cool little thing called simulators. Okay, this is a really fun thing to use. Just a fun fact. So we have 2 objects. Let's color them. Let's color them a bit, like a while ago. Let's color this blue. Let's color this red. There we go. And then we could... Where is my mouse? Where the heck did my mouse go? Okay. Oh gosh, where is it? Here it is. We could... what's our mass again? V1... No. U1 is, I assume, frictionless and no loss of energy. Okay. So the mass of this one should be 2.5. The mass of this one should be single kilogram. And then the velocity of this should be initially 20, right? And this should be initially 30. And then, yep, velocity show values. Okay, so we could see the numbers. This is the only way to make sure. This is an elastic collision. Okay, look, 24.29. Okay, that's the velocity of the blue ball. And look at that. It perfectly matches. And same here for the red ball, 34.29. Okay, we're done. So for reference, okay, if you encounter any elastic collisions in the future, elastic collisions between two objects with a given initial mass, initial velocities, and their masses, you could just use these equations. That okay. I'll end this discussion here now. Okay, at elastic collisions. Maybe next stream we could start discussing. No, no, not start discussing. Maybe we could derive an equation for next time that will determine the final velocities of the objects after an inelastic collision. Well, given that we know by how much the kinetic energy decreases, and right, so you could just copy this. The main star of the yeah. For you just zoom in a bit. Okay, and oh, what's the time? I wonder how long have we been doing this thing? Okay, we've after an hour of discussing some collision impulse, okay, some momentum and collisions. We are finally done. Just right as we were about to run out of board. So that concludes today. As always, you could ask me on Messenger or just down in the comments after I upload this stream, as in the archive for reference. So yeah, that's it for today, and I have no outro, so I'll just end it abruptly, I guess. Yeah, that's pretty much it.